All right, new day and another laptop that needs to be saved, and this time we have an Alienware 17R4. The customer says that this one doesn't charge the battery, and he bought a new charger, and when he plugs it in, it shuts off the charger, so now he's being told that it's a bad motherboard. I haven't taken a look at this yet. We're gonna look at it together and see if we can get this figured out. All right, the first thing we're gonna do is just check to see if it powers on, and it doesn't do anything. Let's plug in the charger and keep an eye on our power meter, see what it does. Okay, and instantly the power meter shuts off. So the machine probably has a short on the main power rail, and what that means is it's putting the AC adapter in protection mode. So this happens whenever the laptop's trying to protect itself, and so it tells the AC adapter to shut off. And so because this is a genuine charger, it will shut off instantly, but if you have like an aftermarket charger, you can actually cause a lot of damage because it won't shut off when it needs to, and then you can send extra current through the board. On these machines, they are older. What I have seen is that the MOSFETs on the CPU, they fail over a period of time. So after, them being in service for so many years, the MOSFETs start to fail and get stuck on, and then sends the voltage from the main power rail straight through the CPU. Main power rail is like 19 volts, and the CPU only operates at like 1.2 volts. So you can end up damaging the CPU. So there is a chance that this motherboard won't be repairable, but we're going to open it up and take a look inside. Okay, it looks like we are missing a screw already. So I'm sure somebody's been in here trying to figure it out. And I don't know if this has been at other repair shops, but usually if somebody sends it over to me, that means that other people have already looked at it and couldn't figure it out. All right, and the bottom is off. Ooh, look at this one. Oh my gosh, this one has a huge heatsink. I mean, it is popping out above the surface here. Let me see if I can get it at a good angle, you can see. Yeah, it's like popping out above the surface, and I'm surprised that the bottom even goes on. That bulges just a little bit. And it also has an SSD here. The problem with this board, like for testing things, we have to take this entire bottom cover off in order to access the motherboard. So I'm gonna have to continue taking this apart to look any further. We can see where the DC jack plugs in, and we can see where the battery plugs in, but we won't be able to measure. All the power circuitry that we're trying to get to is about right here. So let me get this bottom cover off. Now again, I can see some evidence that somebody has taken this apart before. We are missing some of the screws here, and then this Tron light wasn't even plugged in. Now the cause is probably not from somebody taking this apart. It probably failed at some point, but the original note was saying it wasn't charging, and then they bought a new charger and then it shorts out the charger. But I don't know if it was shorting out the charger before they bought the new charger, or if them saying it doesn't charge means that it shorts out the AC adapter. So just have to investigate and take all of our clues while we're doing this. Yeah, like even this wire is routed wrong. This antenna on the Wi-Fi card is not supposed to be routed through here. It's actually supposed to go through this little slot here, and so it's not installed correctly. Okay, we got more screws missing. Here's another one missing here. It's not a big deal. When I put this back together, I'll put all the screws where they go. I have extra screws. These aren't bolted in on the corner. These are the Tron lights that actually light up the whole back cover or the sides, and they're not screwed in on either side. All right, so we got the middle frame. Looks like we have an aftermarket battery in here. This machine is older, so like I don't even stock batteries for this, so you have to go aftermarket. That's not a big deal. Here's the power circuitry here. Like I said, we have the DC in jack here. We have the battery here. There's two MOSFETs on this side. There's going to be two on the other side. These have a tendency to go bad. The first ones go bad if there's a short on the board. So after we actually resolve this short on the board, the laptop won't charge the battery still because we have to change those MOSFETs out. And a lot of times we'll have a burnt component over here, or we'll have one on the other side of the board. But if it is going to be on the CPU, we'll know automatically when we measure this current sense resistor. This current sense resistor is on the main power rail, and so whatever ohms we're getting on there point to what thing is actually shorted out. So we'll be able to know pretty quick. So let's go ahead and get under the microscope. All right, so I have our meter in continuity mode where the probes will beep if you touch them together. And we're just gonna start by measuring from ground, and we wanna follow the input here. So here's the DC jack, and we can touch here. This is gonna be the positive side, the 19 volts, and this is the ground. So these pins are gonna be the ground. This is gonna go through these two inductors right here. So you see the voltage is going to come through here, through these two inductors, then it's going to go through this MOSFET, and on the other side of the board there's another MOSFET that's in parallel with this one, and then the output of these are going to go into this MOSFET. So we're going to measure here, we don't have a short, we're going to measure here, we don't have a short, and then it's going to go through this MOSFET, and then it will come out and we'll go to this current sense resistor. This current sense resistor is on the main power rail, and we measure here, and we are measuring a short. Now based on what ohms reading we're getting on this is going to help us determine what is shorted. Because it's beeping, I'm going to turn off the beeping so we don't have to hear it. But so what are we seeing here? We're seeing 0.2, okay? So 0.2 is almost a dead short. I'll show you here. If I touch my two probes together, we're basically getting the same 0.2, 0.3. So because there is resistance in these wires, so I would call that a 0 ohm short. Now 0 ohm short is actually a good thing, because that means it's probably a capacitor or something like that. But there is a chance that it still could be the GPU at this point and not the CPU, which is also a good thing because if the short is going through the GPU, we can just disable the GPU if it ruined the silicon, and then we'll be able to just still be able to use this board. But so I am actually happy to see that. If we did see like a 2 ohm short or something like that, 1.9 to 2.5 or something like that, then that would point to a short on the CPU, and then most likely the CPU would be dead at this point. Because the AC adapter is shorting out, it means that this MOSFET's probably shorted across. So if we measure here, yeah, so if you see how this is measuring 0.2, so this is measuring shorted across. So basically, the way these MOSFETs works, they work more like a switch, right? It's an on-off type of thing. So we have voltage going in, and then there's a gate pin that turns on and off the MOSFET. So right now, the MOSFET is set to be on, and it's set to just send the current straight through it. And because it's not shutting off, it's just allowing the current to come right through and then go to whatever device is shorted. And so it shorts out the AC adapter instead. The way that this circuit's actually supposed to work is that the power management chip is going to measure current on this current sense resistor, and if it sees an overcurrent, it will shut these MOSFETs off. But because this one's been protecting this board so many times, then now it's actually stuck on. And so this MOSFET or the other one on the other side is bad. We usually just replace both of them as a pair because they've been taking all this current every single time it's trying to protect the board. So, and I can actually see, it almost looks like this current sense resistor is bubbled up a little bit on this solder. I don't know if someone's messed with this or not, but I don't see any heat evidence on any of this other stuff. So that's interesting. I mean, it's not like it's going to be bad or anything, but it's just something to note. I'm not going to be able to find what's shorted on this side of the board. Most likely it's going to be on the other side of the board, but I always like to pull out the motherboard all the way. And that way we can take a look around and see if we see anything physical. And if we don't see anything physical, then we'll do some voltage injection and look under the thermal camera. And then once we put this back together, we're going to want to re-thermal paste everything anyway, and the fans are actually connected to the other side of the board, so we have to take the board out anyway. So let's go ahead and get this motherboard removed. Now I'm going through and unplugging everything. So if you have this model of laptop, 17R4, 17R3, and the 15R4 and the 15R3, not the M series, just the regular 17 model. If you have this model, there's a tendency of people ripping off the LCD connector. So I'm going to show you where it is. It's on the other side of the board. So nobody ever comes and looks on this side. So they'll unhook everything on the other side. They'll pull the motherboard out and they'll end up ripping this LCD connector off. So what I want to do is I want to pre-disconnect this now. I want to do it now before I forget. And then that way I don't have to worry about ripping that off. So I'm just going to unplug that. This is the power button connector, and then this is more, I think, Tron lights for the LCD here. So I got that all disconnected so we don't have to worry about that. All right, and since we already have all that other stuff disconnected, this motherboard is out. All right, so everything looks to be in good condition. I'm not seeing any obvious signs of really discolored areas. Sometimes you'll see a lot of heat spots or discolored components, so everything looks good right now. But we're gonna take a look around. Let me just remove the heatsink while we're at it. That way we can really diagnose this. We're gonna re-thermal paste this anyway at the end. All right, and when you take off heat sinks, especially ones that have been on there for a while, don't pull straight up, just kind of rock it back and forth. It will break it loose, and then you should be able to lift it right off. All right, and I see that they put liquid metal on here. Okay. Everyone knows how I feel about liquid metal. We're not seeing anything major going on here. I'm probably just going to put this heatsink back on after we look around real quick and not even going to mess with it. If they want liquid metal on there, I'm not putting it back on there. So I'm just going to look around real quick on this side, then we'll put the heatsink back on to protect the components because I don't want this leaking anywhere. Liquid metal is good for 10 years or whatever it is. I don't condone it. I don't want to have anything to do with it. I think that's overkill for this board in general, but that's just my take on it. So, all right, I'm going to set this off to the side so we don't spill it anywhere. Let's just take a quick look around on this side while we have this open. So what we're going to look for first is we're going to look for any discolorations or anything burnt or cracked. So these little capacitors right here, you'll end up seeing them cracked a lot. It's going to be on the main power rail, whatever it is, but it could be something that's feeding another power rail too. All right, so we have no short there. This is the power rail that we have a short on, right? Right here, yeah. So all this is shorted. These capacitors are shorted over here. The other side of the board will have shorts on there too, so we're going to look on the other side on there in a second. I want to put the heatsink back on so we don't get the liquid metal everywhere. But I want to measure the CPU. So if we measure the CPU coils, we have, oh, it's 0.2. It's showing the exact same measurement. That's interesting. It's usually a lot higher than that. So we may have a short still here, and I actually see somebody's been in here. Is this right? Did somebody actually change out some of these MOSFETs? Look at these resistors. Yeah, somebody's been soldering in here because A, this kind of looks like flux in a way, and it could just be the thermal pad oozing stuff, but you see this extra solder on these components here? Somebody has been in here. Huh, that's interesting. I'm going to grab another board because it shouldn't be 0.2. So here's another motherboard, and we're just going to measure the CPU coils on this one, and I'm going to show you what it should be measuring. See, it should be measuring 3.6. Usually on a CPU, you'll get between like 2 and 3 ohms, so this one's measuring 3.6. So on their board, we're measuring 0.2, which is basically 0. And on the GPU, we should get a lot lower, like almost 0. Yeah, so 0.1 is what I'm measuring on this GPU. So that's correct. But on their board, we're measuring 0.2 right here. So why are we getting such a low reading here? And to me, it almost seems like we have multiple faults. It's kind of a strange thing to think about, but if somebody else has been messing with this, we could have multiple faults. So what I'm thinking, and this could just be, I'm just off the cuff here, right? So I don't know. Our main power rail has a short that's a 0.2, okay? So it's basically 0, all right? And somebody else worked on this board and they think that it's a short on the CPU, and so they change out MOSFETs and it shorts to the CPU after that. I don't know. Or a MOSFET's failed and another component's failed on the main power rail. Because to me, it almost seems like one of these MOSFETs are actually sending voltage through to this coil. So the main power rail is somehow connected to this coil here through one of these MOSFETs. But the CPU should not be measuring 0.2, right? So the CPU would not be what's bringing it down to 0 ohms, basically. So what we have to do is I need to identify which component is actually causing this 0.2 short, but we also want to bypass this going straight through the CPU. And so we're going to have to do a jumper off of this coil to make sure that we're not going to have any current going straight back to the CPU. So I'll probably end up shorting this back to ground, or we'll actually hook our negative of our injection tool on there. But I want to continue looking around. You know, we're taking note of all these things. This is, you know, it's kind of a strange one, and it makes it more difficult whenever somebody has worked on this ahead of time. So I don't know the exact story. Again, people only tell me what they tell me. So they told me, hey, it doesn't charge the battery. I bought a new charger. It shorts out the AC adapter. That's all there is. There's nothing else that happened. So you can obviously see someone's been in here. They put liquid metal on this, and you can see that there's soldering going on. So it's been to another shop, right? So let's finish our little once over here, and then we'll do our voltage injection, because that's what we're going to do next. All right, so there's the CPU MOSFETs. We're going to mess with it shortly. That's just a BIOS chip for the TPS chip, which is a PD controller for the USB-C. Here are the MOSFETs on the NVIDIA graphics. And there's our beautiful liquid metal that I hate. And I hate it because it gets everywhere. So it's not that it doesn't function well, it's just that it's not worth the risk because it's highly conductive. If they can make something that like liquid metal that's not highly conductive and not going to spill everywhere, then I think I would be an advocate for it. Okay, this is for the VRAM. And then this is, I'm not sure. Let me measure over here. We got 100 ohms, that's fine. Let's see what the VRAM is doing. 0.9, so we know it's not shorted to that, right? So if we're trying to match up what it's shorted to by measuring these coils, it helps. This one's 40 ohms, probably chipset. There's the chipset right there. Let me take out these memory sticks, get them out of the way. All right, I'm gonna look over here one more time. I may have missed something, but because it's almost 0 or dead short, I really think it's a capacitor somewhere. So, has someone soldered this too? Look at this. It looks almost like that's been soldered. That's a BIOS chip of some sort, but it's not the BIOS chip. It's somebody who didn't know that that's not a BIOS chip. So this is a 25Q80. 80 is only a 1 meg chip. It's going to be for something, usually it's for smaller things, PD controllers and things like that. So that's nothing you're usually going to extract BIOS information off and rewrite. It usually won't prevent the board from turning on. Yeah, I don't see anything else over here. And I want to flip this board over to look on the other side, but we have this liquid metal. So I'm going to put the heatsink back on just while I do that. All right, I'm just putting a couple screws in here just to tack it on while I flip it over so it doesn't spill everywhere. If they want their liquid metal, we'll keep it on there for them. All right, so let's take a look on the other side. So I'm going to start over here next to the EC chip. This goes over to the I/O board. It's like a USB board. And we have a power switch built on here. I love that. I love when manufacturers do that. They don't put them on all of these Dells, but sometimes they do. So the power switch, that's the E&E chip. So this is going to be the EC chip. This is what's listening to the power button press. That's why it's always going to be right next to it. They have a tendency to go bad, but that's usually if the programming gets corrupt. And that's all BIOS related usually. All right, a couple of MOSFETs here. Let me measure these. We still want to see if we can find the rail that's shorted. 4 ohms. We got 0.1. So 0.1 over here. So we'll measure on this side 0.3, and on this side 0.4. So this is shorted across whatever that is hooked to, right? It might be the main power rail, but so anyway, yeah, we'll have to take note of that. So that's shorted across whatever power rail it's hooked to, and it's probably the main power rail though. We're just looking at all these little tiny chips, capacitors, things like that. Resistors generally I'm not worried about. So this is the opposite side of the board where the DC jack is. And so I believe this is the one that's paired up with the other one that's on the other side. So I said that those are shorted. So if we measure this, it's shorted on. It's shorted on. So right now it's just sending voltage straight through here no matter what it does. It's not, the on-off switch is broken. Now when I say it's shorted, some people will think, oh, it's shorted to ground. That's not what we're doing. This is actually in line. So we have voltage comes in and it comes out the other side. So it's just shorted on, and then the voltage comes right through. This one's actually shut off though, right? Yeah, see this one's shut off. It's measuring a high ohms rating. We're at like 200 kilo ohms. So this one's stuck on, so it's basically voltage comes through here, and then this one's stopping it. But it's still shorting out the AC adapter. And this should be on the main power rail right here. Yep, and that's shorted. This is going to be the power management chip, the BQ chip. This one's in charge of running these MOSFETs here and then charging the battery. It's usually fine in this situation. All right, all that looks fine there. Let's look around closer to the back of the CPU and GPU. Sometimes we'll find that's where our cracked capacitors are because there's a lot of heat over here. And is that a crack? What is that? It's a hair. Never mind. It looked like a crack, didn't it? All right, but these are directly behind, I believe, the CPU. And so sometimes I'll see them on these 3 pairs here, like this. But I don't see that. Those are fine. Here's the LCD connector. This is the connector that gets ripped off a lot, and I'm proud of whoever opened this up and did not rip the connector off because it looks like it's fully secured still. That's the power button. All right, and then we got to look at the back of the GPU here. All right, so since we didn't see anything obvious, we're gonna have to use voltage injection. If you've seen me do this in the past, so basically the gist of it is I'm gonna inject some voltage into the main power rail or the power rail that's shorted, and we're gonna monitor it under the thermal camera, and whatever's actually shorting to ground will get hot. Now, we want to make sure that we're not going to be sending voltage straight through the CPU, and if we are, then we need to keep our voltage low because we don't want to end up damaging the CPU. I have tricks on how we can bypass that, but we're going to start out with just a low voltage. We'll figure out what gets hot. If the CPU is getting hot, then we'll bypass the CPU, and then it will short straight to whatever component is bad. But let me get the thermal camera set up, and then we can continue. All right, I have my Fluoro Pro set up. It's just attached to the bottom of the microscope here. I have an extension cord plugging in, and then it just shows it on my phone here. And then I just cast it to the screen so you can see it. You could buy one of those. I have a link in the description for all these parts that I'm using. All right, so we are going to use our voltage injection tool. The one we're going to be using today is a short killer. I can set the voltage low. I can't adjust the current on this one, but I love how it beeps and makes a lot of noise and racket whenever we are injecting voltage. So we're going to start out with a low voltage of like 0.5. I always start really low, especially if the ohms is like near 0, then you don't need very much voltage because the current will actually come through here. So 0.5, and then let's go to that. We know that the current sense resistor is shorted, so we'll just do it there real quick. And you see there, even at 0.5, we have 1 amp going through there, okay? Now the question is, do we see anything getting hot? Let's see if we can look around while we're holding that on there. What I want to look at first is we want to look at the CPU. Is the CPU getting hot? I'm going to let go. I do not see the CPU getting hot. But do I see the chipset getting hot? No. See, some of these things are reflections. Like over here, it kind of looks like a reflection. If I tilt it, then it will come and go, and that's how you know it's a reflection or not. It's just reflecting to the light that's above it. All right, I'm going to rotate the board a little bit more. I'm going to hold it in an angle. Let's see. Sometimes you have to adjust the lighting. Okay, here we go. You ready? GPU is not getting hot. Is it one of these MOSFETs getting hot right here? Maybe right there. What do you think? Now we're doing very low current and low voltage on purpose because we don't want to damage anything. But I think we are seeing something right there. And the CPU is getting a little hot, maybe. Holding it down again. Yes. All right, so look around the CPU. It's getting a little warm. And then you can see this MOSFET right here, or whatever is right in this area, is getting hot. Okay, so we don't know exactly if it is this MOSFET or not, but most likely the current's coming through here and then going to the CPU. Now, like I said, I see some stuff going on here, and it could be the fact that the CPU could actually be shorted to ground internally, and that means it's completely dead. A lot of times what happens is you'll see this MOSFET right here will be shorted. I just changed that out. It fixes the short. Then when the machine turns on, it will give a 2-1 error, which is just a failed CPU. But we could have an internal short in the CPU, and then we're done anyway. So now we're going to bypass this coil. So whenever it comes out of the coil, instead of it going to the CPU and actually trying to power up the CPU, we're going to bypass it. So the way we do that is, right now I actually have the short killer's ground hooked over to this ground over here. But that means it has to come through this MOSFET, through that coil, through the CPU, back to ground to get to this ground. But what I want to do is I'm just going to move this and just have it as the output of this coil. And then that means that it will come through this, through that MOSFET, through that coil, and straight to this ground, bypassing the CPU, but it will up the current immediately. You'll see a big spike in current, and so it should be actually higher than 1 amp when we do this. And then it will light up like a Christmas tree, whatever we're looking for. So I'm going to hold it on the back of this coil. These are all tied together on the output. This one, I think these 4 are, but especially these 3 for sure. So I'm just going to hold it on the back of this, and then we're going to do that injection again. Oh my gosh, now we're pulling 5 amps out of there. And do we see which one's getting hot? You see how hot that's getting now? And the CPU is actually being bypassed altogether, so we're not getting any heat in the CPU. That's all what you're seeing coming out of my hand. But the CPU did not get any heat, so we're protecting the CPU, but we're able to see exactly what's getting hot. And so it is that one right there. Let's put some alcohol there and we can see it evaporate. So I'm going to put some alcohol on these. There you go. Do you see it evaporating? So this one right here is bad for sure. So we're going to take this off and then we'll see if the short's resolved. Now it should be resolved, and it could be something just internal in this MOSFET that's causing the main power rail to be shorted back. But again, we could still have a short in here. But I'm going to take this off, and then hopefully that will resolve the short everywhere, and then the CPU could be fine. I don't know. I'm actually, let's see, what percentage will I put on this? Whew. At this point, because I'm measuring that 0.2, so I'm measuring a short in the CPU, I would probably put it at like a 15% chance. But we could get surprised, right? Let's remove this MOSFET real quick, and then we can continue. Okay, this board's very thick. It's going to take a while to heat it up. I'm going to add a little bit of flux. See if I can get this solder flowing. Now, you can see that people have been soldering in here, so I don't know if this has actually been replaced or not. But we are definitely going to replace it, but first we'll just take it off to see if it resolves the issue. So almost there. There we go. All right, we got it off. So this is an SIC 632. I do have some of these. But first we want to test. We want to see if the short is resolved. I'm going to let this cool off for a second, and then we'll test. All right, so let's check the current sense resistor now. And if I measure on the current sense resistor, we are getting, we're getting 50 kiloohms, which is perfect. So the short is resolved. Now the question is there a short in the CPU? So Now I'm going to measure the output coil, and I want to see if we're still getting 0.2. If we're still getting 0.2 on the output coil, then we have an issue with the CPU. Because again, we should actually be measuring something like 3.5 ohms, like we measured on the other motherboard. But if this is a higher end CPU than the other motherboard, maybe it should be like 2 ohms. So this output coil right here, these are all in parallel. I mean, I can measure on this one. Should be measuring higher. We got 1.2 ohms. 1.2 ohms. Okay, so that's better than it was getting. 1.1 ohms. Perfect. Okay, so we actually might be okay. So this may be a higher end CPU. And so ohms are like 1.2, which is fine. Not a big deal. Look at this. Look at this. I hate this stuff. Oh my gosh. This is what I'm talking about. There's no reason. Okay, here we go. We got liquid metal right here. Because when you put a barrier here, this is supposed to be a dam, or all this stuff is supposed to protect this from leaking out. So really, the ideal barrier is like a big foam barrier. Some people will put like nail polish, I think, around the edge. Basically, liquid metal, when it gets hot, it starts leaking and moving around. And so we actually have a couple drips here. One right there and one right there. And I don't know if we have any more. And I don't see these things touching two things together, so it's not that that is going to be the short. Because that'd be interesting if that's what our short was the whole time. But again, I don't see the purpose of this. I may call the guy and say, hey, can I take this stuff off of here? Because I have some PTM 7950, it will get you like 99% of the way there, or 95%. I mean, you don't need this stuff. If you want a peace of mind, you just don't use it. So I'm probably going to give him a call. Oh yeah, so I don't trust it. Don't trust it at all. Okay, let me see. I'm going to have to try to pick these things up. We're going to have to get them cold. I'll probably just put some freeze spray on this, and then we'll pick those up off of there. But I don't want to blow them around is the problem, so let me see. Okay, got some freeze spray on there. Let's see if we can pick those up. Still liquidy. Let me get it colder. Okay, got one, but see, like it's still like instantaneously becomes liquid again. This stuff just gets everywhere too. It's hard to pick up. Okay, there we go. Got that one picked up. This very easily could have went under the CPU too, for all I know. Especially if we have drips there. See, it's hard to pick up these last little drops. I'm not sure what I'm going to be able to do on that. Yeah, because we could have something under the CPU. I don't really see evidence of it, but I got one of these pokey Q-tips. So it just kind of smears around. If I put alcohol on this, it makes it worse. So what I'm going to do, let's replace this SIC 632. I have more of them, like I said, some new ones. And then I'm going to call the customer, and then I'm going to see if he will agree to allow me to take all this junk off of here. And they will probably end up having to ultrasonic cleaner this board just to get all the rest of the stuff off of here. But I'll do a quick test to make sure it posts and stuff like that. But let's put this new chip on here. I'm going to look at these pads. We want to get these cleaned up first. So we're going to clean it with alcohol. And I'm wondering if someone had changed this out and maybe they were shorting out two pins together. Because I'm trying to figure out if this looks like factory solder on here or not. I mean, again, we saw this evidence here, so maybe somebody had already been in here and changed that out. But we could still, you know, maybe we have drips of this liquid metal going under the CPU, like right there. Look at that. See, look at this liquid metal trying to sneak under there. Look, there's more under this side right here too. If you want liquid metal, think twice. So we're going to have to somehow get that out of there too. All right, let's get this on. I'll stop ranting. All right, some fresh flux. We're going to put some fresh solder on there. All right, we don't want too much underneath because we're going to have to squeeze that out. So I'm going to try to pick up any excess. All right, here we go. So we have some new SIC 632s. And whenever I install new chips like this, because sometimes it's hard to get the right amount of solder on these pads. I always pre-tin these pads, and then it makes it a lot easier. So let's do that real quick. So these edge pins are going to be the ones that I mainly need to make sure I get plenty of solder on. The middle pads will always end up having enough. There we go. All right, now that that's pre-tinned, it makes it a lot easier to install. And so pin 1's this top corner right there. That's what we're going to pay attention to. All right, and pin 1 on here is located right there. All right, so this is how it's going to install. We do have a lot of extra solder underneath we're going to have to squeeze out, but that's okay. So I'm going to hold this in place. We'll heat this up and get it installed. This board will take a while to heat up, so we're going to wait till the solder is flowing before we put the chip on there, because we don't want to overheat the chip. Okay, I can see the solder starting to melt. That's when it's time to come bring this guy in. We'll set it down, and it should set down where it wants to go, but we do have a lot underneath, so it does have a tendency to want to move in a different spot. We're going to add a little bit of flux. We'll reheat it up again, see if we can get it to sit properly. Okay, there we go. That's where we want it. Okay, now that's sitting in the right spot, I'm going to let it cool off for a second. I'm going to hold down the center, and we're going to squeeze out all that excess solder. You see all that solder that came out? And we'll move away, let that cool off, and then we'll use our soldering iron to wick away all the rest of that. All right, that looks good. Let me just clean it up a little bit. Okay, it's pretty clean. You know, if I can convince this guy to ditch this liquid metal, then we'll run this through the ultrasonic cleaner and get everything cleaned up, so it will look a lot better when it's done. The question is that short gone, right? That's what we're trying to figure out. So we will measure in continuity mode again, and let's measure the main power rail. Main power rail is showing a kilo ohm rating, so no short anymore. So that's good news. We don't know if the CPU is good still. We don't know if that's been resolved or not, so we're gonna have to figure that out. I guess we can do a quick reassembly. What I hate is that we have that liquid metal there. So actually, let me call the customer. Let me see if I can convince him to ditch this liquid metal, and then we'll put PTM 7950 on there, which does an excellent job. So I'll be right back. All right, try to get in touch with the customer. I just left him a message. I'm just going to do the executive decision here and just remove all this liquid metal. It's not worth it. We'll put PTM 7950 on here, which is much better anyway. So let me peel off this electrical tape that they were using as a dam, and then we could try to clean underneath the CPU. We're going to have to take all this off anyway because the liquid metal got where it's almost leaking under the CPU anyway. So, okay, we got the dams removed. Let's look a little closer and see what we're worried about here. Yeah, so you see these drips. So there's a drip right there, but what I'm looking at is this drip that's going underneath the CPU here. So we can take a look and see if we have anything else under there, but it's exactly the reason why I don't like this stuff. All right, we're going to get close and look underneath as much as we can. So it looks like it's just right under the edge there, but it's not necessarily dripping under and touching any of the pins. It's just really hard to collect it too. We could try freezing it again. That's probably what we're going to have to do. All right, so I'm going to try to freeze it. There we go, got it. All right, I'm going to get this last stuff picked up. But you see when I'm trying to pick up all this stuff, it just kind of collects into a ball. And it's very hard to make sure that you get it safely picked up. So I'm just going to collect it into a pile, and I'm going to hold the board upside down and we'll drip it into the trash can. There we go, it just drips right into the trash can. So we'll do the same thing on the GPU also. Okay, we got it all collected in the middle here. And now we'll just hold it upside down and drop it into the trash can. All right, now I have a new Q-tip. See if we can get the rest of this picked up. I'm gonna send this through the ultrasonic cleaner, and then we can make sure that everything is clean, brand new like factory. Now we don't even know if this board is working or fixed, but what I don't want is to have the risk of having liquid metal on any component shorting anything else, because you can see there's always some residue. We're gonna do our best to try to clean it ahead of time, and then we're gonna clean it thoroughly. But you see how dirty all this is? There's so much flux on here. And I even cleaned the area that I was working on, but whoever was working on this before left a lot of flux residue, so we're gonna get all that cleaned off too. Okay, we just need to take the last of these components off of here before we put it in the ultrasonic cleaner. All right, the board is ready. Let's get this board in the ultrasonic cleaner. I already have it preheated up to 60 degrees C. We use this Bronson fluid in here, and it's distilled water. We're putting it in one angle, and then we'll run it for 2 minutes, and then we'll run it the other way for 2 minutes. All right, we're wrapping up this. The ultrasonic cleaner is done cleaning the board, but what we have to do after we take it out of here, it's covered in distilled water and the cleaning fluid, but we need to displace all that water with an alcohol bath. And so what I like to do is I'll just hose it down with plenty of alcohol, and this will actually wash off all the distilled water. We don't want to leave anything on there that will allow it to corrode or anything like that. And once I have this thoroughly dried and clean, then we can continue testing. All right, we got the motherboard out of the ultrasonic cleaner, and it looks almost brand new. Look how clean it is. So we're hoping that we got all the liquid metal out of any areas that it's in, and let's measure the main power rail. Let's make sure that we're still getting a good reading there. So we're going to measure on this current sense resistor, and we are measuring kilo ohms, which is perfect. So we don't need to worry about it being shorted anymore. Let's go ahead and reassemble this machine and test to see if this CPU did survive now that we've changed out that MOSFET. I will need to clean off the liquid metal that's on this heatsink here. And to test, I'm just going to put on just regular heatsink compound, and then if everything's working, then we'll put on our PTM 7950. All right, so this is another reason why I do not like liquid metal, especially on systems that aren't designed for it. So here's the heatsink, and we're going to try to clean this off. And I want to show you what it does to the heatsink. If the heatsink's not designed to take liquid metal, it actually eats through the copper. Gallium, this is a gallium-based liquid metal, and it reacts with aluminum, and I'm assuming that this copper isn't 100%. Yeah, I'm never going to be able to get this all the way clean. It doesn't look like. And you see the shape of the CPU die has actually been imprinted in here because it started eating away at the metal. So now this has an actual texture to it. See how this is smooth? This is scratchy. There's actually some stuff still stuck in here. So I'm going to have to keep working on this to see if I can get this clean, but this takes so much more time. And it is actually slowly destroying this copper plate here. Same with this one. Same thing, it's all scratchy. It's not smooth anymore like this. Smooth, scratchy. I mean, get a load of this, trying to get this stuff off of here. I'm just sitting here scrubbing it. If you try to wipe it, nothing happens. And I'm scrubbing hard with this Q-tip. It's just because it's almost like fused with the metal underneath, eating away at it. I'm not even sure liquid metal existed when this heatsink was created in 2017, but maybe so. All right, that's about as good as I'm going to be able to get these. They still have a texture to it. So any heatsink compound we put in here hopefully will smooth that out. And then since this is liquid metal, hopefully it will smooth out when it gets hot. But we're gonna have to go with this. That's the best I can do. Or we're gonna have to replace this heatsink, but we'll figure that out whenever we run our tests and stuff. But really, we just want to figure out if this machine works or not. All right, so I'm just gonna put some Arctic silver on these chips for right now, and then we'll come back and put the PTM 7950. All right, we got the motherboard installed, and the question is it gonna work? I put a low percentage on actually this being able to be resolved, but we will see. Okay, we plugged it in. We got 0.01, that's a good sign. So we're not shorting out the AC adapter anymore. So let's see if it actually will power on. Power button. And we are pulling current for a second at least. If it will come back on. 0.02. Do I smell something? Let me try it again. 0.43. Oh, I smell something. I smell something. So right as I press the power button, it turns on for 1 second and then shuts back off. Okay, 0.02. That means that the LDO and the EC chip's turning on. That's a good sign. Let's try it again. Press the power button. And now we're getting nothing. So a second ago we were getting, it jumps up to like 0.43 and then shut off. Oh, 0.54, okay, for a second, and shut back off. And I thought I smelled something, but when I did it again, 0.54, shut back off. 0.45, so it doesn't have anything to do with me pushing the power button. So something's trying to trigger on, and it's shutting back off. Okay, this is a strange one. We're gonna have to measure while we're looking underneath here. Let's see how far the voltage is going. Now, considering we're getting 0.02, that usually means that we have the LDO turning on, which is the linear voltage regulator that powers the EC chip. So let's put this in voltage mode. And this is coming out of the DC jack. We have our 20 volts coming out of these MOSFETs. And then the current sense resistor, we have our 20 volts on our current sense resistor. Now, I do see a drop here, though. That's something to think about. We have 20.17 going into this MOSFET here. Now let's get under the microscope. I can show you closer. So here's coming out of the DC jack. We have 20 volts, 20.17, right? 20.18. That goes into this MOSFET, and out of this MOSFET, and into this MOSFET, and we have 20.17. But then on the other side, on the output, we're getting 19.61. So we are missing about half a volt. Somewhere in here, the half a volt's being lost. And usually what you should see is the same thing we're seeing on this one, where we have 20.18 here, and 20.18 coming out. When this is on, it should be on. So we may have an issue. We know that these are shorter. There's some issue with that one, but I'm not worried about that because the machine should work fine, just doesn't charge the battery. But this one actually has a drop on here, or we have something that's dropping voltage on this power rail here. But we're seeing a constant current draw of 0.02, but that shouldn't pull down that half a volt. The LDO, I'm trying to think of where that is. Can't remember. Is it over here? Those are 3.3. So our main voltage rail now is 19.61 instead of the 20.17. And what I want to see is what's spiking, getting hot for a second whenever we turn it on. But I can't do it with this board in here, and we're going to have to get back under the thermal camera to take a look at that. But basically, when we're seeing it jump up to 0.54 and then shut off, 0.54 and shut off, I want to see what component's getting hot. It's probably trying to turn something on and seeing some sort of short and shutting it back off. And it could be something like the CPU or something like that. Because again, we did see some sort of short in the CPU area. It did end up being caused by that MOSFET, but and now that short's gone, but it's still a strange symptom. So let's go ahead and pull this board back out, and then we can continue testing. All right, I have the motherboard removed for the second time. I just have a separate DC jack. That way we can plug it in and test when it's out of the system. And we'll get that connected. All right, so when we plug it in, we are seeing that 0.01, right? 0.02, 0.01. And then you remember we had that power button we could trigger on the board, which is nice. So let's take a look at that. Yeah, so right here next to the EC chip, we have a power button switch. We can actually just trigger the board on, and we can take a look at the power meter and see what it does. 0.54, and then drops back down. So ideally, it should jump up for a second, then go down to 0 again, then come back on at like 1.5 amps or 2 amps or something like that. That's the normal startup process, especially after the CMOS battery's been removed. But since we are just jumping up to 0.54 for a second and shutting off, you see it just went to 0.18 by itself too? That's definitely a strange one. And so let's turn on the thermal camera, because with it doing that, we're going to see something getting warm on here. So here's the EC chip. We should see that warm because that should be on. But I want to see what's spiking up to 0.54. That's what we want to see. Let me reset the power here real quick. Okay, I'm going to plug it back in. Okay, we have our 0.1. I'm going to trigger the power button. Let's keep an eye over here at our MOSFETs for the input circuit. And I'm triggering on the board now. 1, 2, 3. 0.58. Did you see anything spike up for a second? I didn't see anything. See if we can try it again. It's only for a second, so it's kind of hard. Hey, the fans came on for a second. I just saw the fans spin. And so now when I push the power button, nothing happens. So it's like it's after that initial trial where it's trying to turn the board on, then it says, okay, I don't want to try turning this on anymore. No, but the fan just spun again. Just missed the fan spinning. All right, let's flip it over and see if we can see it on the other side. Okay, I have the board flipped over. Let's keep an eye over here. This is the main input circuit. All right, I'm just going to try to trigger it on. 0.61. Fan spun for a second. We're just getting a quick burst of power. See, the fan spun again. Let me unplug the fans. I don't know. I doubt we're having a fan issue, but I want to unplug the fans and take them out of the picture in case we're having some sort of issue with that. Let me reset the power again. I think that we probably have another shorted rail somewhere. We might need to go around and measure all over again. 0.2. And it could just be the CPU's bad. I mean, I'm going to take the heatsink back off so that way we can actually see if the CPU is like spiking with heat real quick and then shutting back off. Okay, the heatsink is off. Let's figure out if we can see if one of these MOSFETs are getting hot or if the CPU is actually spiking with some heat. Okay, let me see if I can trigger it on real quick. Okay, you ready? Up, yep, the CPU spiked for a second and then shut back off. Now, whether it's the CPU is bad or not, I don't know. So let's measure the voltage on the CPU rails. So I'm measuring one of the coils right here on the CPU. Just keep an eye on the CPU. I'm going to turn it on again. There it goes. It just spiked for a second. Yeah, I'm thinking that this CPU is toast. Usually on this machine, whenever a CPU does fail, it's usually just one of these MOSFETs are bad, and then I replace it, and then the CPU would just give me an error, but it will turn on like normal. But this looks like there's a short in the CPU. Right as it tries to turn on the power rail for the CPU, the system is detecting too much current going through that current sense resistor and immediately shuts off those MOSFETs. So I think that's going to be it on this board. I don't think this board is going to be repairable. This is going to be a candidate for a board replacement, but I'll let the customer know, and I'd love to know your thoughts on this one, and thanks for watching.
I couldn't save this laptop.